Yeah, thanks for coming. So I'm very pleased to hear Marcin Briański who will talk about coloring, right? Coloring
yes.
and string graphs and
String graphs, Burling graphs, and
yes.
High-boundedness.
Yes.
All right. Hi all. So this talk is based on joint work with Tara Abrishami, James Davis, Xing, Jana Masarzykowa, Paweł Żążewski, and Bartek Walczak.
Can you write that?
I will write it when I get to our results. It will take us a while. All right. So the story begins with the notion of chi-boundedness. So just so that we are all on the same page, let me quickly give you a definition of what I'm talking about. So a class of graphs and here a class of graphs will always mean a hereditary class of graphs, meaning that whenever I see a graph for my class, any induced subgraph will also land in that class. I will just omit this from this talk because I would then say hereditary all the time. So we'll call it chi-bounded. If there is some function of natural numbers to natural numbers, such that for any graph in my graph class, graphs, graphic G, we have a chromatic number of this graph is bounded by a function of its clique number. Okay, so it's a notion. It was introduced by Gyarfas in 1985 as a generalization of perfect graphs. So let me give you some examples to stay concrete. Well, since it's a generalization, good generalization generalize. So perfect graphs. Yes, so those are our graphs G, such that for any induced subgraph we have chi of this, the chromatic number of this subgraph equal to its clique number.
H.
Yes. Thank you. Yes, so in particular, perfect graphs are chi-bounded with the function being the identity function, so best possible. In a sense, these are the most chi-bounded class of graphs you can possibly imagine. Okay. But to be a generalization, something else should also be chi-bounded. Well, and this second example I will give is a very common topic, which we'll hear more about during this talk, is this geometric flavor of class of graphs. So for example, intersection graphs of axis-aligned rectangles in the plane. So this is 4, 5. So they're not perfect, because this is, for example, an odd cycle, C5 in the graph class. But they're chi-bounded with chi of any such graph being at most some of omega g times omega of g. Yeah, there are many ways to generalize this. We could look at other spaces like R cubed or other shapes like maybe strings. Yeah, so it's a very, very rich and deep topic of research into such intersection graphs. Okay. And the third example I would like to give you is the sort of intuition that simple graph classes should be chi-bounded. So what is a good measure of simplicity is maybe with parameters. So for example, graphs of clique width at most some constant, or twin width most some constant. So most width parameters I am aware of give you a chi-bounded class of graphs if you look at ones with bounded such width parameter. Now, another very deep topic is seeing how forbidding local structure, like a and specific induced subgraph, influences a global property like chromatic number. So, for example, graphs with no induced path on k vertices. This is actually one of the examples from the original paper of Garfash from 1985. And this is very, very well connected to the well-known Garfash-Sumner conjecture that states that this should be true for any forest, not just paths. Okay. So those are examples. And as I said, these somehow we should think of those graph classes that are k-bounded as somewhat simple. So there are some graph classes that are not k-bounded, right? And how would you argue that a graph class is not k-bounded? Well, simple. We just have to find a sequence of graphs G1, G2, that are all members of our graph class, such that the clique number or any graph in our sequence is some constant, but the chromatic number of graphs in our sequence diverges to infinity as we increase the index in our sequence. And somehow in practice this constant is most commonly 2, meaning that we usually look at triangle-free graphs and we obtain a sequence of triangle-free graphs with increasing chromatic number, showing that for our specifically chosen graph class there is no well-defined f of 2. Yes? Not always, but usually. And also there are recurring examples of graphs that people use for this purpose. Yes? You may be familiar with some of those, like tax graphs, or shift graphs. But during this talk, the most important example will be the Burling sequence of graphs. So I will call these graphs B1, B2, and so on. So I will define what, I will tell you what these graphs look like later during the talk. For now you can just think of some very specific sequence of graphs with without triangles and increasing chromatic number. And as we shall see, it's a rather complex sequence. It's not something obviously with something obvious. So a bit of history. They were introduced by James Burling in 1965, so before even the notion of k-boundedness was formalized. And they were kind of forgotten for close to 50 years, but have been living through a renaissance since around 2010s, and have been since used as a counterexample to many conjectures connected to chromatic number. Specifically, they were, I guess I should say, rediscovered in the so-called 7 poles paper by Pawlik, Kozik, Krawczyk, Lasso, and Micek, Trotter, and Walczak, where they showed that all Burling graphs are string graphs. So what is a string graph? String graph is an intersection graph of curves in the plane. So I can obviously create many different graphs. In this way, it's a rather rich class of graphs with problem of recognizing a string graph being very difficult, and so it's a rather complex class of graphs, but it's not infinitely complex. We can say some things. For example, we can say that they forbid induced subdivisions of specific graphs. If I take a k-free and I subdivide every edge once, then k-free is not planar. And an induced subdivision being realized as a string graph would give me a planar embedding of k-free. So this is, so string graphs forbid some induced subdivision of certain graphs. Yes. In particular, realizing Burling graphs as string graphs, I think this proved two conjectures at once. First of Erdős from 1970s, that such I think he was asking specifically about segment graphs, but in particular, the construction from the paper realizes Burling, any graph from the Burling sequence as an intersection graph of segments, not arbitrary curves. And the second one was the Scott's conjecture, which asks whether if I take any graph and forbid all its induced subdivision, will the resulting graph class be k-bounded? And, well, the answer is no. Okay, so why this specific graph class? Well, because since that example appeared around 2012, people have spent time investigating string graphs further, and we were unable to find any other counterexample, which led Chudnowski, Scott, and Seymour to the following conjecture. Let G be a class of graphs and excluding induced subdivisions of some fixed graph F, F for forbidden. Then for any T and N, there exists some constant C, such that for any graph from the graph class with sufficiently high chromatic number, so more than C, one of the two conditions must hold. Either I find a KT as a subgraph in my graph, or I find the nth Burling graph in the Burling sequence as an induced subgraph. And well, this is rather a difficult to believe conjecture, and the authors themselves rather say that they have little faith in this conjecture. And I think this was more said as a provocation, like find me a completely different construction of graphs that forbid some induced subdivision and are not k-bounded, completely different from Burling graphs. Okay. Well, somewhat surprisingly, there's a theorem. So I'll now state the theorem and then explain the statement later. Show me. Baby. let G be a graph class forbidding subdivision of F, forbidding induced subdivision of some fixed graph F, and 2 controlled. Then the Chudnovsky-Scott-Seymour conjecture holds for this graph class.
So you're forbidding all subdivision, all induced subdivisions of F, right?
Yes. Yes, so you can think of this graph class being, for example, string graphs. Yes, as we've seen, they forbid this induced subdivisions of once subdivided K33. Yeah, so I wanted to tell you the general statement, but mentally you can just substitute string graphs whenever I have some graph class I'm considering other than the Burling graphs. Right. So we are able to actually prove this conjecture under this extra assumption of 2 controlled. Okay, so I should tell you what 2 controlled means. This definition. So we have some graph class G, and we'll call it 2 controlled. If the following condition holds, if there exists a function from natural numbers to natural numbers, such that for any graph in my graph class, chromatic number of this graph is bounded by a function of the largest chromatic number I see in a tuple of this graph. So this means that the chromatic number is sort of always high chromatic number among graphs in this graph class is always certified by bounded radius graph with still large chromatic number. And this is maybe a bit of a technical condition, but this is actually extremely useful when trying to establish that a given graph class is k-bounded. In fact, we can define this notion to be more general, where in R control we just look at the balls of radius R. Yes. And it is not hard to convince yourself that chi-boundedness is equivalent with being 1 controlled. Okay. And there's another theorem due to Chudnovsky, Scott, and Seymour. String graphs are 2 controlled. In particular, since all Burling graphs are string graphs, this also applies to Burling graphs. So, using this, we can derive some consequences. Well, the first consequence that I like the most, actually, one is that the class of Burling graphs is minimal in the following sense. The chromatic number of all Burling graphs is unbounded. Yes, there are Burling graphs with arbitrarily high chromatic number. But as soon as you forbid any one of them as an induced subgraph, so you take a proper class that sits inside all Burling graphs, the chromatic number becomes bounded. Yes? By our theorem, it applies because string graphs are two controlled, so Burling graphs are two controlled, and they exclude a subdivision of induced subdivisions of once subdivided K33. Well, the first point cannot hold because Burling graphs are triangle free, so this also holds for all induced subgraphs, and I just forbid you from the second point holding, which means that the chromatic number of any graph I'll see must be bounded by some function, by some constant. Yes. So this is not the only example of a minimal class of graphs, but the only other known examples are cliques, where this is sort of trivial. If I forbid a clique of size k, I'm left with a finite collection of cliques, those of size less than k. Okay. The second observation is that KL coloring is polynomial on string graphs. Well, for any choice of k and L large enough. What is KL coloring? Well, it's the following promise problem. This. So you're given a graph G, and your task is to distinguish the following two cases. First one, chi of G is at most k. Second one, chi of G is greater than L. Yes. And if I look at the string graph and think in terms of the result we have here, to check that the first case cannot hold, it suffices to look for a k plus 1 clique or k plus first Burling graph as an induced subgraph. Yes. Either one of those will prevent me from being in case 1. Yes. Well, and if I don't find them, then by this result, chromatic number is at most some constant. So if L will be larger than this constant, I cannot be in case 2. Yes. So I can just brutally enumerate all possible candidates for a Burling graph, all possible candidates for a clique, and determine in which of the two cases I will land.
So this problem is to decide whether chromatic number is smaller than or equal to k or bigger than L.
Yes. So this is from the promise constraint satisfaction world, where this problem is, I think, conjectured to be NP hard for all values k and L, where L is at least k, on general graphs. Well, on string graphs, even though it's a fairly complex graph class, this turns out to not be the case.
Don't you need the L to be like
Huge. Yes.
something, right?
Yeah, like some huge function of k. But for any k, I will be able to find such a.
No, isn't L should be, so do you want L to be smaller than k or?
No, k should be always smaller than L. Yes, and if you hold k constant as L increases, the problem should become easier and easier to solve. So in light of this theorem, this tells us that Burling graphs are kind of a universal obstacle to high-boundedness. Yes? Because if I have a graph class that forbids some graphs induce subdivision and is too controlled, then it will be high-bounded if and only if it forbids some Burling graph. If it contains all of them, it will not be chi-bounded because f of 2 will not exist. And if it forbids one of them, by our result, it will be chi-bounded. All right.
So you say too that if we forbid some, if we fix some 3t and excluding all the induced subdivision of these 3t, then is it true that this graph classes is two controlled? Then if this is true, then this would be the relaxation of the Jarfas-Sumner conjecture.
Yeah, Jarfas-Sumner is not about subdivisions of tree.
Yeah, but
If you forbid subdivisions of a fixed tree
yeah.
in your graph, then this is chi-bounded. This is a theorem due to Alex code.
Do you know anything about graphs that are not two controlled?
Yes, there is something known. For example, there's a theorem, and I think this is again Trudnowski, Scott, and Seymour, that if I have a graph class that forbids induced subdivisions of some fixed graph f, and is R controlled, then it is 2 controlled. So these notions collapse if you forbid some induced subdivisions of any fixed graph. Yes. And there is also a conjecture.
So you can put R controlled in your theorem as well, then, right? Or is there something wrong?
Yes, but yeah.
Yeah, you just consider two controlled, right?
Exactly.
Yeah,
Conjecture, and here I would say Scott and Seymour, that any graph class forbidding induced subdivisions of some graph f is 2 controlled. And prior to our work, I think this was a rather believable conjecture. Now it's unclear because clearly this conjecture implies the Trudnowski-Seymour conjecture now, in light of this result. And what are your feelings if reasonable conjecture seems to imply unreasonable? That's difficult to say. All right. So I think at this time I would like to tell you what Burling graphs actually are. So I will follow the original definition that was used by Burling. So I'll define a sequence of graphs together with a sequence of independent subsets of this graphs Bn. And independent sets. So the beginning is very simple. That is B1. And the first family of independent sets consists of just singleton of this element. Okay. So how to build Bn plus 1, assuming I have already built Bn together with Yn? Well, we start with a central copy of Bn. Yes. And now for every element of the family In, so it lives somewhere here, I introduce another copy of Bn, isomorphic copy, just for this one independent set. And now for every set Y in the family of independent sets for this isomorph of Bn, I add one new vertex, v x, y, adjacent to every element of y. Yes. This completes the description of the next graph in a sequence, but to complete the construction, I also need to tell you what the new family of independent sets looks like.
Wait, so is B, so do you have like no edges between Bn and Bnx, or?
Yes. So this graphs in this sequence are always disconnected. But the induced subgraphs are not. And indeed, in the next step, when this will be the peripheral copy for some set, I will connect them in some specific way. Okay? So, what are the independent sets I will consider? Well, I take x union y, so this set plus this set, for any x from the central copy and y from the corresponding peripheral copy, together with sets of the form x with this new extra vertex vxy. Okay.
So you have a one, you start with a central copy, and then for each independent set in IN, you make one copy.
Yes.
For each independent set.
Yes. So it may be instructive to go through
Uh-huh.
first few steps. So first I start with just one vertex being its own independent set. Well, then how does B2 look like? I start with the central copy of B1. I add a new vertex here and a vertex adjacent to it. And my new independent sets are these two. And then for B3, I have two peripheral copies. And now I add a vertex here. That's because those were independent sets from the previous step. Yes. And as one can see, this has chromatic number 1, 2, 3. So it stands to reason that the chromatic number will increase in each step.
By induction?
Yes, we can induct. And inductive statement is that in any proper coloring, f of Bn, there will be an independent set in IN such that f uses at least n different colors on this set. Yes. So it clearly holds for B1. Yes, I use some color on the vertex. And now let's take any coloring, and we find here the set X from the central copy, where we are using n colors. So there are n colors used here. And actually we can say that this is exactly n colors. If there are more than n colors, we are done. Yes. Well, I can also use the inductive assumption for the peripheral copy. Peripheral copy of Bn and find the set Y. And again, there are exactly n colors used on this set. If the two sets of n colors are the same, well, are different, then the union of x and y is a good choice.
Mm-hmm.
Yes, I will see at least n plus 1 colors then. And if they are the same, then the color of this guy must be different than any color that appears here, because any color that appears here also appears here. So in this case, x plus this guy is a good choice. Okay. So it is easy to see in this in this definition of Burling graphs that the chromatic number grows in each step. If one goes a bit more carefully, one can even argue that fractional chromatic number will grow not by one, but by half, if I remember correctly. But this is not a very good definition for our purposes. So we actually derived a sort of new characterization of Burling graphs. Yes, one of the strengths of Burling graphs is that they have a lot of equivalent definitions. This is work mainly by Pournajafi and Trottignon, where they were able to find characterizations such as derived graphs, so graphs coming from some tree, or as strict frame graphs, so intersections of very specific objects in the plane. Yes, but we needed a new one. Okay, so this definition will be in terms of graphs with some specified set of specified independent set of vertices, which I will be marking in red, which will be called active vertices. So the starting graph we'll have is simply one inactive vertex adjacent to one active vertex. So let's call this maybe V1 star. And we'll have access to one operation which takes a graph with active vertices. I'll call this operation double. Graph here. And we have some set of active vertices. Takes another copy of G with some same set of active vertices, just an isomorphic copy. So G. You now can select any one of those active vertices and add a twin to it and connect the twin to all active vertices in the other copy. Okay. So this looks like at first glance to be completely unrelated, but actually it is not that hard to argue that all graphs created in this way are Burling graphs. In the sense that they appear as an induced subgraph of one of the graphs in the sequence I told you.
All graphs created this week from Burling graphs?
No, from edge with one active vertex.
I see. Sorry.
So
no worries.
the active vertices don't change when you do this operation?
Yes, the new active vertices is the union of active vertices here and in the other copy. And any Burling graph appears as an induced subgraph of a graph that can be obtained in this way. From edge with an active vertex using double one. And this is, so there were previously known characterizations of Burling graphs using active vertices and operations involving active vertices. So this is not something completely new, but it is new in the sense that there is just one operation involved, and it is rather simple.
Perhaps you don't have the property the chromatic number increases by 1 and this
No.
covers no.
In fact, because by counting this will not happen. This operation doubles the number of vertices, and chromatic number of Burling graphs is on the order of log n. So you sometimes need exponentially many of those operations to just bump the chromatic number by 1. Okay. So let me give you an overview of how does the proof work. So we are actually using approach very much inspired by work of Trudnowski, Scott, and Seymour, and it is using something called multicovers. So we are given a graph. So assume you are given a graph from the graph class, which we assumed is 2-controlled, of absolutely huge chromatic number. So how does this help us? Well, we can use the 2-controlled assumption to find the vertex, and let's assume the graph is triangle free. So there are no edges here. This has chromatic number 2 so far. So its second neighborhood here must still have a huge chromatic number. Yes? And there are no edges from this top vertex to this box on the right. But this is an induced subgraph of a graph from my class. So again, I can apply the 2-controlled assumption here. And this will still have pretty huge chromatic number. So I can continue in this way to extract this sequence of sets, all dominated by a single vertex, that all cover some set with still pretty big chromatic number. Well, and actually if one is a bit more careful, this extraction can be done in such a way that between this vertex and these vertices, either I have all possible edges, or there are no edges appearing here at all. So this is called
No edges appearing where?
no edges between this bottom set here, this supporting set, neighborhood of this apex vertex here, and later apex vertex.
That means the later apex vertex is actually in the neighborhood?
In the neighborhood of what?
Wait. Like
So-
your box on the right, this is the neighborhood of the ellipse, right?
Of this, yes.
Yeah.
This supports this entire set, but I can restrict the attention here to a subset and possibly kick some vertices out.
Ah, okay. You don't keep.
So
Sure.
I can maybe explain this in how to perform a single step.
Okay, I see.
No, if you don't keep the left, it makes sense. So,
Yes, I can restrict this. So the step is performed as follows. You find this set that supports something of still large chromatic number, and now this vertex divides each of those sets in two. In the vertices that are adjacent to it, and vertices that are not adjacent to it. And for each vertex here, I ask, do I have a neighbor in this set? Okay, then I write here 1. If I don't, that means that I have only neighbors in the other set, so I will write 0. So if this sequence had length t, I now have a 2 power t improper coloring of this set. And since this set has huge chromatic number, by sacrificing a fraction of 2 to power t, which will be a constant, we'll be only considering multicovers of bounded depth. there will be still a subset here that is monochromatic under this coloring. Yes? So everybody here has a neighbor in this part, neighbor in this part, and in this part, so I can safely discard the other set and keep only working within this set. In this way, I've made sure that any pair involving the freshly added guy is either independent or skew with all previous pairs. So I extended this tidy multi-cover, tidy in the sense that interaction between bottom part and top part is well controlled, by 1. So continuing this manner, I will be able to find as long multi-cover as I want, as long as the depth is constant in terms of clique number in generality and the Burling graph I'm looking for. Okay. So there is this very interesting idea, because in the work of Trudnowski, Scott, and Seymour, they were able to show that if you find a long independent cover, then you can find any fixed graph as a subdivision in your graph, as an induced subdivision. This in particular means that we can apply Ramsey's theorem to find in any very long tidy multi-cover either a completely independent multi-cover or a completely skew one. But the first case cannot happen because we assume that we are forbidding some subdivisions of some fixed graph. So the only case that is left to consider is the skew case. So this vertex here on the top is always fully adjacent to this set that appears earlier. Okay. And this seems like a very useful structure, and I will try to show you how to get not completely induced subgraph, Burling graph as an induced subgraph, but I will get rid of some of the edges and make sure that all required edges are there. In particular, this is already enough for at least some of the consequences I drew on the board. For example, for the second one, if you find the Burling graph just as a subgraph, it is still a certificate of high chromatic number. Okay, so there is a tweak that we need to do to this multi-cover extraction. So let us fix, so we are looking for some nth graph in the Burling sequence, and by the lemma we can find a sequence of graphs V1 with active vertices such that each next graph is obtained via double from the previous one. Maybe we are looking for kth Burling graph, and BK is an induced subgraph here. So I will call a copy of DI well spread. So grab some colors. If the following happens, we can find a sequence of sets and a final set at the end, which I will call the set of anchors. And I want to see a copy of DI that has all inactive vertices here, and for any choice of this set here, there is a representative of every active vertex from my DI. So say I had 4 active vertices here, so I need to see 4 active vertices in each one of those bubbles, and any choice of representative of an active vertex here gives me a copy of the I in the graph I'm working on. Okay. So assume we have extracted a multi-cover that I don't necessarily yet know whether it is skew or independent, because that I will derive at the very end from application of Ramsey's theorem. So but I know that the depth will be bounded. Yes, if this has depth t, I will never go beyond some function of the length of this doubling sequence and the size of forbidden independent cover that you get from work of Trudnowski, Scott, and Seymour. Okay. So this t is always bounded. So I see here, for any choice here of the supporting sets, let's call this family A, and any vertex here, I will record some information. Call it precolor of V. This will be, again, a binary vector indexed by a family of subsets here, and the index in the doubling sequence. So I will say that this set is set to 1 if for any choice of set of small chromatic number, so you can delete sets of small chromatic number from this world W, and there still will be a well-spread copy of DI hiding somewhere here with all inactive vertices in W minus the small set, and all active vertices having representatives in each of the blue bubbles. So in each bubble from the set A, that are moreover all adjacent to V. So this should be a well-spread copy of DI for this to be set to 1. So this is fairly complex information. It tells us somehow that this W is still very rich with respect to the multi-cover we have defined so far. And if it doesn't exist, so for some small set, you can remove it and kill all copies of DI, we'll just record this as 0 in that component. Okay. So this is again some improper coloring of W. So I can now restrict my attention to a monochromatic component of still high chromatic number and work only within that. So here now I'll extract the multicover, the two-ball that still has high chromatic number, then apply the tidying step and continue within that. Now repeating this pre-coloring part. And how is this useful? Well, assume one more thing I need to do. Once I am happy, I have found this pre-colored this monochromatic set and this vertex here. Well, it has some values within this coloring. So for every value that is 0, so whenever there is a small set that is hard for this vertex, we just remove it. This is a removal of bounded number of sets of bounded chromatic number. And I remove it from this part here. Okay. Yes. Okay. So now assume that we have found ourselves in the skew case And the length of this multi-cover is at least n, where n is the length of the doubling sequence that we started with. This is Q, maybe let's keep drawing remaining edges. And here I am still supporting something of high chromatic number. Well, if it's supporting something of high chromatic number, then in particular I can see a vertex there. Well, this vertex is supported by each one of those sets. So I can find a neighbor here within each one of those bubbles. And this is now a well-spread copy of D1. Yes, because D1, as a starting graph in the doubling sequence, is just a vertex adjacent to one active vertex. Okay. So now when I look at the set of high chromatic number I was working with when extracting this guy, and this support set might be now a bit enlarged, I see a well-spread copy such that of D1, such that I have here the set of representatives that are all adjacent to the top vertex here. So precolor at this step of this vertex X with respect to this this specific family of support sets and index in the construction sequence 1 must be 1. Because if it were 0, then I would have removed a set of small chromatic number that should kill all copies of all well-spread copies of D1. And I see here a well-spread copy of D1. But this vertex, this particular one, is also selected from the same set as X. So its precolor value is the same. So I need to be able to find here always copy of D1 even after removal of a set of bounded chromatic number. So I can remove neighborhood of each of those red vertices and of this white vertex, because this is a bounded number of neighborhoods, this has bounded chromatic number, and I need to be able to find here a well-spread copy of D1. Yes. And moreover, it needs to be fully adjacent to V. But this is a well-spread copy of D2, because I just performed the doubling with respect to this active vertex. Yes. So repeating this argument now with respect to this world, I will see that precolor value of this vertex, let's call it X prime, will also need to be set to 1 for D2 this time. So I will be able to remove neighborhoods of all red vertices and all white vertices I keep track here. And I still should be able to find a well-spread copy of D2 with respect to choice of this vertex or this vertex, because now I have two active vertices. This will enable me to perform another doubling of my graph. So continuing in this manner, I will at the end produce a copy of the n. Okay. So that's all I wanted to say today. Thank you.
Thank you. Any questions?
So I have two questions.
Yes.
First is how control are controlled. So the string graphs are the example of two control graphs, which is not one control.
Yes.
So do you have another example for general R that is for each R? Is there a graph has a graph that's R plus one controlled, but not R controlled?
No, I do not know such an example.
Oh, even for R equals 2. So is there an example for 3 controlled, but not 2 controlled?
Yes, I don't think there is such an example now. So it is an open problem to find a graph class, hereditary graph class which is R controlled but not R minus 1 controlled.
And the second question is about this Burling induced subgraph. So it is just think of a similar for cliques. So if you have a graph and an integer k, you can just check if the graph contains a kth Burling graph as induced subgraph. But let's say the Burling number of a graph is a maximum I, such that it contains ith Burling graph as induced subgraph. Then do you know about the complexity about calculating the Burling number of a graph?
Not really, no. Like until very recently, it wasn't even clear if you can recognize Burling graphs in polynomial time.
Oh, I see.
I think this has been since resolved that this is doable in polynomial time.
Oh, I see.
But finding the largest induced Burling subgraph, I have no clue.
Would you know reference about the recognition of Burling graph?
About
The
what?
reference about the recognition of Burling graph.
Oh yes, this is a paper by Bartosz Walczak and Paweł Żążewski. It's on archive,
Okay.
and it's I don't remember the title.
Okay. I'll say sorry. Thank you.
Other questions? Are there some interesting classes other than string graphs that have this forbidding some induced subdivisions of fixed graphs?
Well, I think that Burling graphs themselves are interesting case.
They are string graphs, right?
Yes. Well, an interesting case I think is forbidding induced minors. So if you have a graph class which forbids an induced minor, this is a stronger assumption than just forbidding an induced subdivision. And I think in general, to control is unknown for these graphs. There is stuff related to asymptotic dimension that also gives you forbidden induced subdivisions, but I don't know much about it.
Any other questions? No. So if not, let's thank the speaker.